When I want to think about the growth of a function, I really want to compare them. Once I can figure out how to compare functions, I can figure out how to apply this to algorithm. So while this seems like a switch in topics, I promise it's really not. So let me start with this question. Which is bigger, x squared or x cubed? Why? Okay, but 1/2 squared is 1/4. 1/2 cubed is 1/8. The square is bigger than the cube. -2 cubed is -8. -2 squared is +4. The square is bigger than the cube. All right. The real problem with this question is that I didn't tell you where. And without knowing where, I can't really answer the question properly. So I really want to think about you being correct, Blake. How do I make it so that you're correct? The cube is bigger than the square. I think about what's going on when x is large. So really, I want to compare functions in limit. This is why we need calculus for this course, so we can think about this as limit terms. I'm thinking about this really for large values of x. The idea of measuring functions was put together in several different places. The most commonly used notation today is by a guy by the name of Landau. It's called the big O notation. And it represents a bound above. So if I've got two functions, I'm going to say that f of x is in the category of being bounded by g of x. By saying that it is big O of g of x. And we'll write that as a function, big O of g of x. We can also say that f belongs to the group of functions. So sometimes we'll write f is an element of the set, big O of g. But what does it mean to be this? This is what I'm going to call it. What's the definition? If I can find a way to make f less than or equal to some multiple of g. Once I get out far enough. Okay, means I need two numbers. I need to know how far out I need to go, and I need to know what multiple. So I need two numbers, c and k, constants, with the absolute value of f of x is less than or equal to c times the absolute value of g of x when x is strictly larger than k. This reads like it was written in Farsi. I have no idea what this is talking about. You've got to be kidding me. This makes sense? Wait a minute. The C and the K are called witnesses. And my goal is to, for each possible function, figure out how to get this inequality and where I need to be to make it happen. All right. This sounds just too abstract. Let me do an example. I am going to claim that the function x squared plus 2x plus 1 is big O of x squared. I got an idea. Let's start with an assumption about our x values. Let's go out a little ways on the x-axis. Let's go out to x equals 1. If I know that x is bigger than 1, well then I know that x squared is also bigger than 1. Yes? Because if you take a number that's bigger than 1, you square it, it gets bigger. If you take a number that's bigger than 1 and you multiply both sides of this equation by x, I know that x squared is bigger than x, right? I just multiplied both sides here by x. With me so far? Now let's look at f of x. Remember, my goal is to show this. The hell did you just do, Sassmore? I had a 1. I know that x squared is bigger than 1 whenever x is bigger than 1. I had an x. I replaced the x with an x squared. I know it got bigger. These two things are bigger than these two things. So this whole side must be bigger than this whole side, as long as x is bigger than 1. But this side, that's just 4x squared, isn't it? Hey, wait a minute. F of x is less than or equal to number times g of x. I have a C. I have a K. I found my witnesses. It worked. Why did I get rid of the absolute value part? Colin? When x is bigger than 1, all of these things are already positive. I don't have to worry about that part. Now, as soon as you find one set of witnesses, it is possible to find other different sets of witnesses. Witnesses are not unique. I could have said, let's let x be bigger than 5. Well, then I could have said different things about this, right? Here's another version of the same problem. Suppose x is bigger than 2. Well, then 2x is less than x squared, isn't it? I multiplied by x on both sides. I also know that since x is bigger than 2, x squared will be bigger than 4, which is definitely bigger than 1, isn't it? So now I could say, let's take f of x and replace each thing by something I know is bigger. I'll replace the 2x by x squared. And I'll replace the 1 by an x squared. So now I have two different witnesses. C is 3, K is 2. As soon as you find one set of witnesses, you can find others. Questions? Were it my choice, I'd do this first one over the second one because I don't have to pick it just right to make this work. I know as soon as I'm bigger than 1, I can do all of these sorts of things. But that's me. Sometimes our choice of witnesses depends on how we build this chain of inequalities. Now, my first reaction upon looking at this, that thing on the left, that's a division problem. That f of x, x squared plus 1 over x plus 1, that's a division problem. And I'm claiming that's big O of x? What the? I'm going to start the same place I started that one. Let's suppose x is bigger than 1. This time, rather than multiplying on each side, I'm going to add on each side. Isn't that a true statement? The thing on the left can be factored. What happens if you factor the thing on the left? If I divide, I get x squared plus 1 over x plus 1 is less than x. I've just shown that f of x is less than 1x whenever x is bigger than 1. I found my witnesses. Graphing calculators, graphing devices, graphing programs on your MacBook. I want you to graph this. We're going to graph that, right? Standard window, minus 10 to 10, minus 10 to 10. There's that weird asymptote in the middle, right? What's the rest of it look like? A straight line. And if I zoom out, I can see it doesn't just look like any straight line. It looks like the line y equals x, doesn't it? It looks like the line y equals x. As a matter of fact, if this is our original window, minus 10 to 10, minus 10 to 10, if we graph y equals x right alongside this, you can see they're really getting really close to each other, aren't they? This is a slant asymptote. Do you remember in your algebra class finding slant asymptotes? Not really. Okay, wait a minute. Let's do the division. Do you remember how to do long division? Oh, long division was a long time ago, man. Okay, little short refresher over here on the side. I am going to divide 263 by 12. How many times does 12 go into 2? It doesn't. But 12 goes into 26 twice. So I multiply and I get 24, and then I subtract and I get 2, and I bring down the next number. How many times does 12 go into 23? Once. I multiply, I subtract, and I get a remainder. Right? Let's do the same thing over here. How many times does x go into x squared? Well, what's x squared divided by x? It's x. So I multiply, I subtract, I bring down the next piece. X goes into, well, that'll be a minus 1, won't it? Multiply, minus x, minus 1, subtract. 1 minus a negative 1 is 2. There's my remainder. So I get x minus 1 plus 2 over x plus 1, just like I had plus 11 over 12 here. You know what? This is the asymptote I'm talking about. That's the line I want to use. And it's just a power of x, isn't it? That's what this big O idea is about. It's saying, hey, really, this thing in the long run is going to behave like it was just a power of x. This thing in the long run is going to behave just like it was a quadratic. However, what we are looking at is upper bounds, right? So it doesn't have to be an exact upper bound. Is 7x squared bounded by x cubed? Huh. Let me think about the graph again, because that's really my intuition here is it was kind of like the graphs got related. 7x squared versus x to the third. Although it might be 2x cubed, it might be 3x cubed, might be 0.7x cubed, I don't know. But it's an x cubed. So let's compare these. Zoom, 6, 7x squared, x cubed. It looks to me like the x cubed is on the bottom. Yes? Let's look further, because they were both growing really quickly, right? Let's look a lot further up. This window went from minus 10 to 10 in the x's. 10 cubed is 1,000. So let's put the 1,000 out there. That way I can see all the way to the top. There's my 7x squared. Here comes x cubed. There's a point where x cubed starts to be on top, isn't there? If I can find that point, that's how far out I have to go to know that x cubed is going to be above. Those are my witnesses. How far out do I have to go to make the x cubed one be on top? That, by the way, will have c equal to 1, because it's 1x cubed on my graph, isn't it? Where do they cross? This is actually easier to find by hand. 7. If x is 7, then 7 cubed is the same as 7 times 7 squared, isn't it? But watch what I do with the equations. Suppose x is bigger than 7. Then x cubed is bigger than 7x squared. That's the equation I wanted. That tells me that f of x is less than c times g of x whenever x is bigger than k. Excuse me, questions? What if I switch those? This one? Okay. But then I won't have a witness in the correct orientation. Remember, I need to know that this is true for all x bigger than some number, right? Let's go back to the witnesses. This is f, this is g. I want f to be less than or equal to c times g when x is bigger than k. It's got to be from some point on. And if you reverse it, then you're telling me it's only true for x less than 7. That's not the right direction for a witness. And now is where I say I did something sneaky earlier. I used F is a part of the class of things that's dominated by G. I didn't say it was an equals. This belongs to a category. I think this is wrong. I think x cubed is never going to be beaten by x squares. This is 7x squared, right? Let's make it a bigger number, x squared. Instead of 7x squared, let's double that. And you might say to yourself, well, 14x squared, that's going to be bigger. Yes? Sure looks like it's bigger. Until I go out further. And then my x cubed still manages to cross it. Oh, shit. Just like we said, these were going to cross when x was 7, because 7 times 7 squared was the same as 7 cubed. If I keep letting x get bigger and bigger and bigger, then I'll have an x squared times some number. I don't know what the number is. But when I get past that point, won't x be bigger than that? So x cubed, which is x times x squared, would be bigger. Oh, okay, hang on a second. Let's actually prove this. Suppose x cubed is big O of 7x squared. Then there exists a k and a c with x cubed less than c times 7x squared when x is bigger than k. That's the definition of being witnesses, right, Evan? It's got to be bigger on the right. X is bigger than k. Well, if this is true, I'm going to divide by x squared. So here's the problem. I've just reached a contradiction. The witness tells me it's good from every number from k to the right. And this sentence tells me it's only good up to here. How can I have to be true for everything bigger than this, but I'm not true if I'm bigger than this? Oh, shit. What happens if I pick C to be smaller than K? Or, oh, crap, this is a contradiction. It's got to be true for all X bigger than K and less than something at the same time? I can't do that. That's a contradiction right there. The other way to think of it would be to say that X over 7 is less than a constant. What happens as X goes off to infinity? Infinity is less than a number? That contradicts everything you just turned into the homework about infinities. Infinity don't work like that. This is why you don't write that F equals big O of G, because this is not a symmetric relationship. 7x squared is big O of x cubed, but x cubed is not big O of 7x squared. Not symmetric. Questions? I want to apply this to any kind of function. Some functions are harder to deal with than others. So let's start with the easy pile of functions. Let's start with polynomials. That's what a polynomial looks like. Number times power of x, number times power of x, and the powers are going from highest to lowest. That's not a requirement. That's just how I've written this one, with the highest power first. I claim that this is big O of x to the n. Whatever that highest power is, that's the one that matters. I'm going to prove this. And I think you all could prove this right now. If you went back and looked at our first example, you'd know exactly how to prove this. I'm deliberately not picking something bizarre or weird or all sorts of screwed up or rigged for a witness. I'm going to start with x is bigger than 1. Based on our first example, if I know x is bigger than 1, what do I know about all the other powers of x? And more. I know that x squared is bigger than x. I know that x cubed is bigger than x squared. I know that x to the fourth is bigger than x to the cubed. All the way up to x to the n is bigger than x to the n minus 1, right? Which means I'm going to take our f of x. That a0 on the end, that's a number, right? If any of these numbers are negative, I'm going to replace them by their absolute value. This is definitely less than or equal to absolute value of an, x to the n. Absolute value of an minus 1, x to the n minus 1. Absolute value of a2, x squared. Absolute value a1, x. Absolute value a0. Those are all positive numbers. This one type. That a0 on the end is multiplied by 1 times 1. Now look at this giant list of inequalities right here. This one says that x to the n minus 1 is smaller than x to the n. So if I replace this by an x to the n, I've made the whole thing bigger, haven't I? If I replace the x squared by an x cubed, I'll make it bigger. But if I replace the x cubed by x to the fourth, I'll make it bigger. If I replace the x to the fourth all the way up to x to the n, if I replace this x squared with x to the n, haven't I made it bigger? Same thing with this x, yes? Same thing with this 1. I made it bigger. Aren't those all just number times x to the n? Factor out the x to the n. And you get big ass number x to the n. Let's give this number a name. I'm going to call it C. I have a witness. I have another witness. I found my C, I found my K. every single time. If you have a polynomial, in the long run, the only piece that matters is the highest power. Now, before you look at me and go, this is the most up thing I've done in algebra ever in my entire life, you've seen this before. I want you to go all the way back to the very first algebra class you ever took, where you did graphing. Most of the time that happens in the pre-calculus class. Maybe it happened in your first algebra class where you did lines and parabolas and all that fun stuff. Remember the math dance? Line, parabola, what's x cubed? And x to the fourth, and x to the fifth, and x to the... Only the highest power is what tells me about the ends, right? And since I'm thinking about this as x goes to infinity, I'm thinking about the end behavior. And the end behavior of a polynomial is determined by its first term and nothing else. You did this when we talked about horizontal asymptotes. Rational function, you looked at the highest power on top and the highest power on the bottom. You did that in Calc 1 when we did limits. So I know you've seen this at least there. We've seen this crap before. We just never thought of it this way. Questions? Because this is weird. I don't just have to apply this to a function, f of x. I can think about a function in discrete terms, like a sum. I'm going to define the function f of n is the sum I equals 1 to n of I. So I could be asking you, roughly how big is this sum? In terms of n. Well, if I add up the numbers from 1 to 100, I get 5,050. We did that last 2 weeks ago, right? If I add up the numbers from 1 to 10,000, I'm going to get a lot bigger number, right? 500,500, 500,000. We had a formula for this. What was the formula for this? Wait a minute. That's a function of n, isn't it? Ignore that for the moment. F of n is this. That's the same as n squared plus n over 2, which is 1/2 n squared plus 1/2 n. That means this is big O of n squared. Oops. I know I've done everything in terms of x. Most of the time when we write big O discussions, we usually do it in terms of n because we're thinking about this in algorithm terms, in terms of the size of our input list. Remember the search algorithms? and the sorting algorithms, I said we had this many numbers, and I gave them A1 through AN. So if I tell you how big the input list is, tell me how long it's going to take in terms of N rather than anything else. So frequently, we'll write these as N's. What's that again? Factorial. And that means almost. It's not every integer less than it. It stops at every positive integer less than it. Because if you include all the integers, you got to go to minus infinity. I don't want to do that because I'll hit 0 and then I'll get 0. This is big. Grab your calculators. What's 10 factorial? $3.6 million, right? By the time I've gotten to 10, I've gotten to 3 million. 20 factorial is going to be even bigger, right? (2.4 times 10 to the 19th. Ridiculously large number. I only got to 20. If you do 70 factorial on your graphing calculator, you know what happens? Error. It's too big for the calculator. Calculator only handle up to 10 to the 100th. 70 factorial is bigger than 10 to the 100th. It's ridiculous. How big does this really get? What's a good upper bound? That's exactly what big O notation is talking about, right? N is clearly the biggest number here, right? So clearly this is less than or equal to N times N times N times N times N times N. How many N's are there? There are N of them. Which means this is N to the nth power. That's ridiculously huge. If I think about the way in which things grow, I can actually rank functions. With polynomials, it's easy, right? The highest power tells me how big it is. So x is smaller than x squared, is smaller than x cubed, just like you said at the beginning, right? X cubed is bigger than x squared, it should be. But what about other functions that float around in there? Let's think about the logarithm. Now, if I'm a math geek, I think in log base e. If I'm a physics geek or a sciences geek, I think in log base 10. If I'm a computer scientist, I should think in log base 2. Because everything's in binary anyway, let's do it in powers of 2. I don't care what base it is. This statement applies to all bases. Think about the graph of log of x. What's the graph of ln of x? You have a graphing device. You do not have to do this in your head.
Like comes out and that goes.
right? But where's x? There's y equals x. Which one's bigger? X is bigger. Everywhere. So that's smaller than any power of x. If it's smaller than x to the 1, it's smaller than x squared. It's smaller than x cubed. It's smaller than x. If I had fractional powers like the square root, I just turn it into a 1/2 power. It'd be in between. And as a matter of fact, the square root of x is bigger than x and smaller than ln. Is bigger than log and smaller than x. So fractional powers fit in the middle. I rarely use fractional powers. They're less helpful. Most of the time I'm working in whole number powers. Most of the time. But if I'm really thinking in whole number powers, I can actually stack these. All the powers of x will go in here. Each one times a logarithm. The logarithm is kind of the in between the two powers. But eventually, I get to stuff that's bigger than powers of x. What's bigger than powers of x? Oh, exponentials. And the bigger the base, the bigger the power. And eventually, I'll get stuff that's even bigger than that. On the bottom of page 227, there's a picture. This picture is exactly that list in increasing order. Notice the y-axis on this picture. The y-axis is not linear. It's in powers of 2. That's why the graph of 2 to the x is a straight line. This is a skewed graph. It's got a logarithmic scale here on the y-axis. What happens when I start trying to put functions together? I'm going to use this as the basis to build more complex functions. That's what we'll talk about on Monday. I will see you all then.